Greetings, everybody. Learning is a hobby here. I want to do section 4.2, the summary for section 4.2 in Terence Tao's Analysis 1 book in this video. So let me bring up my summary and we'll go through the notes. Just bear with me for 1 second. All right, here we go. So just one thing before we start, the development of or the construction of the rational numbers in this section follows closely the way that we constructed the integers, in that we first construct the rational numbers as a using an equivalence relation on a set of rational numbers, and then we derive everything from there. So let me start with the definition. So a rational number is an expression of the form a/b, where a, b are integers, and b is not zero. A/0 is not considered to be a rational number. Two rational numbers are considered to be equal. So a/b equals c/d if and only if ad equals cb. And the set of all rational numbers is denoted by the symbol q. All right. There's a note here, exercise 4.2.1 asks the reader to show that this is a valid definition of equality. So we'll do that when we get in the next video, which is which will be the solutions to the exercise set for this section. I'm almost done with it, so I should actually have it posted maybe by tomorrow. I think I have like 2 questions left or 3 questions left or something. Anyway, so we'll do that in the video on the exercise set. All right, next we have definition 4.2.2. If a/b and c/d are rational numbers, we define their sum, a/b plus c/d equals ad plus bc /bd. Their product is it's hard to say / a million times. You just multiply the numerators and the denominators together, right? And negation, you negate, for example, the numerator. And that define those operations on those equivalence classes. Right. Here's a note. If B and D are non-zero, then BD is also non-zero by proposition 4.1.8. Therefore, the sum or product of 2 rational numbers is rational. All right, then we come across lemma 4.2.3. The sum, product, and negation operations on rational numbers are well defined in the sense that if one replaces a/b with another rational number, a prime / b prime, which is equal to a/b, then the output of the above operations remains unchanged, and similarly for c/d. All right, so here's my proof. I do believe he leaves this as an exercise, but I just did it in this in the summary anyway. So here, without loss of generality, assume that a/b is a prime / b prime. Which implies a b prime equals a prime b, just by the definition of the equivalence classes here. So let's go through the different cases. So a/b plus c/d equals ad plus bc /bd, and a prime b/b prime plus c/d is equal to a prime d plus b prime c /b prime d by the definition of that the way that we defined addition of rational numbers. Then if you look at the numerator times the denominator of the other one, that we want to show that that's equal to the numerator of the other one times the denominator of the previous one, right? So that's what I'm doing here. AD plus BC times B prime D is equal, when you distribute, is a b prime d squared plus b prime cd, which is equal to a prime b d squared plus b prime cd by the fact that a/b is equal to a prime / b prime. And that's equal to a prime d plus b prime c in parentheses times bd by the distributive law for the integers. Okay, then for part 2, we want to show that the the products are well defined. So A slash slash B times C slash slash D is AC slash slash BD, and A prime slash slash B prime times C slash slash D is equal to A prime C slash slash B prime D by definite the way we defined multiplication. And then again, you just check that they're in the same equivalence class. So AC times B prime D is the same thing as A B prime C D, when you just reassociate, right? And that's the same thing as A prime B C D, because A slash slash B is equal to A prime slash slash B prime, which is equal to A prime C times B times D by just reassociating again. So that shows that they're in the same equivalence class. All right, and then finally for negation, the negation of A slash slash B is negative A slash slash B, and the negative of A prime slash slash B prime is equal to negative A prime slash slash B prime. And again, just we have to check that they're in the same equivalence class, and you can see here by the calculation that they are. All right, and that's the proof that 11.4.2 is true. Okay, note here, the rational number A slash slash 1 behaves in a manner identical to the integer A. So, if you add two numbers of that form, you get another number of that form. If you multiply, same thing. If you negate, same thing. Also, A slash slash 1 equals B slash slash 1 only when A equals B. Then by identifying A slash slash 1 with the integer A, we guarantee that the arithmetic of integers is consistent with the arithmetic of the rationals. In particular, all natural numbers are rational. So, for example, the definition of the algebraic operations here on the rationals will supersede the definition that we had for the integers and for the natural numbers. All right, so for instance, 0 will identify with 0 slash slash 1, and 1 will be identified with the equivalence class 1 slash slash 1. Also, A slash slash B is equal to 0 slash slash 1 if and only if A times 1 equals B times 0, implies the numerator A must be 0. That implies that A slash slash B is not 0 slash slash 1 if and only if A is not 0 and B is not 0. All right, and then we can define what we mean by the reciprocal of a rational number. If X is A slash slash B, where A is not 0, B is not 0, then the reciprocal of X, which we denote X inverse or X to the minus 1, we'll define that to be B slash slash A. All right. He states as a proposition here, I don't think he proves it in the book, but so I just wrote it out as a proposition and I proved it here in the section like I like to do. So the proposition is the notion of reciprocal of a non-zero rational number is well defined. So here's my proof. Let A slash slash B equal A prime slash slash B prime for A, B, A prime, B prime integers, all non-zero. Then A, B prime equals A prime B by, the way we define the equivalence classes. Consider the inverse of the two numbers there, or the two rational numbers there. Then B A prime equals B prime A implies B slash slash A equals B prime slash slash A prime, and that's the proof. Okay, note the notion of quote unquote numerators not well defined. For example, 3 slash slash 2 is equal to is in the equivalence class 6 slash slash 4. They're the same equivalence class, but notice that the numerators 3 and 6 are not equal. All right. And then I guess he just has a note here. We leave the reciprocal of 0 undefined, right? You're not allowed to divide by 0. Okay, then we have proposition 4.2.4, which is the law of algebra for rationals. Let X, Y, Z be rationals, then the following laws of algebra hold. So we have, the first 9 axioms are similar to the ones we had for the integers, but we have one additional axiom here. And, also the difference is these are rational numbers now with the way that we defined, the operations on them. But there's also one additional operation that we can do now, which is the reciprocals. So if X is not 0, we also have X times X inverse equals X inverse times X equals 1. And all the other, laws should be familiar. So I won't bother reading them through. All right, and we'll prove this theorem, but we'll do it in exercise 4.2.3 when we get to the video on the exercise set. Okay, remark 4.2.5. The above 10 identities assert that the rationals Q form a field. In fact, we'll see in a second, they actually form what's called an ordered field, but the axioms that we have here are for a field. Right. If you remember, the integers formed a ring, in fact, a commutative ring with identity. And in fact, actually, the integers form something called an integral domain, but he doesn't mention that here. And a field, we've actually talked about fields a little bit, I believe, in the beginning of Spivak's book. And when we get to Spivak's book, again, when we start constructing the real numbers, I think the first section in the epilogue is a quick section on fields. So we'll meet this algebraic structure again. Anyway, we can now define the quotient x divided by y of two rational numbers, x and y, provided that y is not zero by the formula x over y is defined to be x times the reciprocal of y. All right, using this formula, it's easy to see that a over b is equal to a slash b for every integer a and every non-zero integer b. Therefore, thank God we can discard the slash notation because it's really annoying to say, and use a divided by b instead of a slash b. Similarly, we define subtraction on the rationals by the formula x minus y is equal to x plus the negative of y, just as we did with the integers. Okay, definition 426, a rational number said to be positive if and only if we have x equals a over b for some positive integers a and b. It's said to be negative if and only if we have x equals minus y for some positive rational y. For example, x equals negative a over b for some positive integers a and b. Okay, our definition is consistent with our definition of positive and negative integers. So, all that stuff carries over. Then we have similar lemma here of trichotomy that we, similar type of lemma that we had for the integers. We have that here also for the rationals. Let x be a rational number, then exactly one of the following three statements is true. X is equal to 0, x is positive or x is a positive rational number, or x is a negative rational number. And we'll prove that in the exercise set. So we'll see that in the next video. All right, definition 428. Ordering of the rationals, let x and y be rational numbers. We say x is greater than y if and only if x minus y is a positive rational number, and x is less than y if and only if x minus y is a negative rational number. We write x greater than or equal to y if and only if either x is greater than y or x equals y, and similarly define x less than or equal to y. We've seen a similar definition for this, for the integers as well. All right, here's the order properties for the rationals. Again, very similar to what we did in the last section, but we have to do them over again for the rationals. So let x, y, z be rational numbers, then the following properties hold. Part A, order trichotomy, exactly one of the three statements, x equals y, x less than y, or x greater than y is true. Order is anti-symmetric. In other words, one has x less than y if and only if y is greater than x. C, order is transitive. If x is less than y and y is less than z, then x is less than z. Addition preserves order. So if x is less than y, then x plus z is less than y plus z. And positive multiplication preserves order. In other words, if x is less than y and z is positive, then xz is less than yz. And again, we'll prove this in the exercise set. Okay, here's a remark that Tao gives us for, he labels it 4.2.10. Propositions 4.2.9 and 4.2.4 assert that the rationals Q form, again, like I said a second ago, they form an ordered field because they're a field and they have an order defined on them. Note, it's important to keep in mind that proposition 4.2.9e, that's the one where positive multiplication preserves order. That only works when z is positive. So, and then he says C exercise 4.2.6. We'll look at what happens if you multiply by a negative number in that exercise. And that's it. So it's kind of a short section because we're sort of rehashing similar types of things, but for the rational numbers. And, we do have to prove them all separately for the rationals because the rationals are not the integers, right? They're a bigger set than the integers. Let me stop my screen share. So because we, defined the rationals as, a bunch of equivalence classes, right? Then we have to just verify that everything works the way that we need it to work. So we'll do like I said, we'll do the exercise set in the next video. It's a relatively short section too. I'm almost done with it, so I should be able to post the video for the exercises tomorrow. And there's just like I said, 2 or 3 more problems left for me to do, and then we'll be on to section 4.3. 4.3 is a little bit long, not that long, but we'll do that one next. And then the last section is relatively short, so we I think if if I'm able to keep up this pace, I think we'll be done with chapter 4 this week actually, so which will be nice because then we can move on to constructing the real numbers finally, which was I was hoping to get to that by the end of July, and we're just a tiny bit over what I was hoping. So we're actually doing pretty good. So let me know what you guys think down below. Give me a like and subscribe if you enjoy the content here. And I'd like to hear from you down below. So let me know if you're going through this book with me. Let me know what you think about Tao's book, and I'll see you guys in the next video. Keep learning, everybody.